Okay, so welcome everybody to the last Heidelberg Joint Astronomical Colloquium of the winter semester. And today we're very glad to be able to invite a familiar figure from the past back to Heidelberg, Glenn van der Van from the University of Vienna. And to introduce Glenn, I ask Nadine Neumeier.
Thank you, Richard. It's a really great pleasure to welcome and introduce Glenn van der Ven, who's actually been a group leader here at the MPIA, also overlapping with me when I was starting here. So we've worked together. So Glenn is a stellar dynamicist, and he obtained his PhD from Leiden Observatory, then moved on to a postdoc in Princeton, and also had a Hubble Fellowship at the Institute of Advanced Study in Princeton. And after that, he became a group leader at the MPIA and also had a permanent position there, but he decided that he wanted to actually go somewhere else. After that, with an ERC grant, he went to ESO, was a faculty member there, and from there he took his ERC grant to Vienna, where he is now since 2019. And in Vienna, he actually established a new graduate school. He was so inspired by the Impress that he actually wanted to have something similar there. So he is the co-founder of the Vienna Graduate School, VISIS, right? VISIS, yeah. And this was established in 2020. And since 2022, you're the head of the department and the head of the astronomical observatory in Vienna, and so have a lot of bureaucratic overhead also to deal with. But I think it's great that Vienna has you now, and it's great to have you back as a visitor. So I'm really thrilled to hear about the colorful past and dark side of galaxies unveiled through population dynamics of their stars. Please, Glenn, the floor is yours.
Thank you. Okay, perfect. Good. So it's really great to be back, to see some actually quite many familiar faces. So today I hope to give you an insight on what excites me and my research groups. And towards the end, also some forward-looking. Richard and Nadine also asked to give a brief motivation introduction, as there were not so many talks about galaxies or galaxy evolution. So I will first start. Let me see. So now I got this, it should use it. Perfect. So I'll just start with a picture that I'm sure all of you have seen. So we have this absolutely wonderful instrument, the James Webb Space Telescope. And of course, before we had many other instruments, because one way to look at galaxy evolution is actually to look at distant galaxies, and because with the distance we actually look back in the past, and this is really great. Yes, so no complaints about that at all, but there's still a but on the slide. As is obvious, the more distant galaxies, they are faint and small, and if you really want to link the evolution from the early universe to now, you have to do this in a statistical way. So in a complementary approach is actually the one that in the group we are taken. And this is to really look at nearby galaxies. For nearby galaxies, we have very precise and detailed information. And here's an example, one of these wonderful, really deep images where you see around this elliptical galaxy, you see all these shells and streams. And so this is really an immediate highlight of the buildup of galaxies over their lifetime. But what you see here in the images are stellar streams of shells, which are actually rather relatively recent accretion events, so like a giga-year ago. And the reason is very clear, is because these stars quickly disperse. And so does this mean we can only look back very recently? And I hope to convince you by the end of the talk, the answer is no. We can actually go pretty far back in the past, but for that we need to do a little bit more effort. And so a little bit more effort is, first of all, we need really, really excellent data. And second, we need the techniques to really take advantages of that excellent data. So what I also put on the top of here is that something that I will try to describe you may sound for many of you familiar is that what is happening in the galaxy, in our own Milky Way, where probably you are familiar with the term galactic archaeology, so that you really try to use the memory in the motions and the chemistry of the stars to rebuild, in principally, what happened with the Milky Way. I will come back to the end and hope to convince you that in our view, we can do this not only for the Milky Way, actually for many nearby galaxies. So what is the type of data? So as an example galaxy, I will show you for this one, it's NGC 1380 or FCC 167. So that means it's from the Fornax cluster. And as you can see from the zoomed in image, this is a rather boring looking, actually lenticular galaxy. And what you see on top of it with these squares, what you see on top of these squares is the footprint of this fantastic instrument at a very large telescope. It's called MUSE, and MUSE is an IFU spectrograph. So what can we do with that? So many things. So let me see if this works. So here, what you see again is the same picture. This is like a description of the ID. It's a different galaxies, just to make sure. Is that what you do with these IFUs is that in principle at every position, I have to go here. So at every position on the plane, you get a spectrum here. So in the end, you have a 3D cube. Namely, at every position, you also have the wavelength direction. And so this instrument is so sensitive that you can get these spectra in very high singleton noise, and you get very, very precise details. And what is shown here is just pieces of the full spectrum, and this is just from one position on the sky. And why showing this as an indicator for those that are somewhat familiar? What we're trying to do is fit these spectra in very much detail to extract the properties of the stars. And what's shown here, because these spectra are many pixels, you can try to fit them pixel by pixel, but typically that is also a very slow process. So within the collaborators, we have devised a technique which is a hybrid between fitting these so-called absorption feeds, where most of the information, but in these absorption feeds are going pixel by pixel. Why stressing this? And you see some reference below. Is because with this technique, it became possible to actually extract stellar population properties across the whole galaxy. So here, for example, you have two examples of what you can measure. So you see the same galaxy. So these are the squares from the footprint, and you see all these small, like the colorful pixels here. So behind every, there has been a spectrum there, and we fit that spectrum, and then we get, for example, the mean light-weighted stellar age of all the stars. And you see that this is a very old galaxy, or the stars are typically old, from 13 gig-a-year down to 10. But you see there's still some variations. Yes, in the very center, it is the oldest, and then it goes slightly younger. And on the right side, what you see is the stellar metallicity. You see that the stellar metallicity is everywhere relatively high, and highest in the center. And the nice thing is now you can really map out, so you can compare, for example, already you see the stellar metallicity is flatter than in the image. So this gives you already information on the physical properties of this galaxy. However, you can, with this quality data and the technique, go much further. So on the left side, you have a kind of indicator, alpha in elements indicator. But on the right side is something that is one of the main drivers why we have been doing this. So this is really getting a handle on actually so-called stellar IMF. So this is really to, in practice, what we're actually measuring there, or get a handle on, is the ratio of low mass stars to high mass stars, or to dwarf to giant stars. So this so-called IMF measurement, this is new. Yes, we were before we were happy if we could do this for one single measurement per galaxy, and now we can start mapping this out. So I hope that this is quite convincing that we can now really get very detailed mapping out of the stellar population properties. So now I want to give you two examples, very recent ones, and one of them not published actually, what you can do with this. So one example you see on the right. So on the left is exactly again the stellar metallicity. Yeah, so nothing. This is the same picture as before. But what we can actually measure is more than just the stellar metallicity. We can go to each position and actually measure what is the spread in the stellar metallicity. And then you would say, okay, what do we learn from that? And what we learn from that is what is plotted here on the right side. So on the x-axis, on the horizontal axis, we have the mean metallicity. So that is the value in this map. And then at each point, we can also measure the spread. So this is sigma squared of the metallicity. And why is this interesting? Because if this galaxy was purely self-enriched, so if it was living in isolation like a closed box, and you have one generation of stars that then is in principally producing the metals from which the next generation is born, then you should grow gradually along this line. And you can make observations of isolated system, and they actually fall very precisely on this line. So it is a very tight correlation. The only one of the major regions why they can deviate, or what's called an over dispersion here, is actually if you have a system and you merge another system with it. So suddenly you merge systems which will typically have two very different metallicities because they are in a different phase of their evolution. And this over dispersion you can then use really to get a measure on, for example, how many mergers what kind of mergers that you have. And so what the PhD student together with Ryan Lehman has done is measure this over dispersion fact at every position of this galaxy. And what you then get is a map on the left. And so on the left is a simulated galaxy. So what we done there, we went to the TNG50, we extracted, simulated, we made mock data, made mock metallicity, etc. I would through the IFU cube, so the whole as if we observed the galaxy. Yes, then we measure this as we would from data, this over dispersion factor. So this is literally how high are you above this line here. And if you then plot this map of this over dispersion factor, you can compare this with what you can measure directly from the simulation, which is a quantity that is very much wanted. It's like how many of the stars are actually ex situ, or how many of the stars were actually born outside of the galaxy and were brought in through a merger. Yes. And so this local ex situ fraction, typically we have already a huge amount of trouble to get a global number. Yes. And like we think we're still quite a few tests to be done, that we can now actually do this with this quality of data locally, meaning we can get map out, like where in the galaxy, how many stars were accreted and how many stars were born locally. Okay, so this really learns us then immediately, of course, about the title of the galaxy. If you get a handle on how many stars came from outside, already starts giving you a handle on how many mergers happened. Yes. And so we want to go beyond, and this already work that was done actually also here. We asked the question, would it be feasible at all to get the full merger history? Yes. Is the stellar population properties that we measure, can we measure them so precise that we can make an argument, at least statistically, that we can find out not only how much, so the ex situ fraction, how many accreted stars, but can we also figuring out from which type of merge they came? So how big were the satellite mergers? And this is what we did at this moment, is still from a theoretical perspective, but we went through the whole cycle again. We took simulations, We made mock spectra out of them. And then it turns out, and this type is from the Eagle simulation, then it turns out that actually going through this technique, that you can actually get a handle on the satellite mass function. So this really, you see on the x-axis is the mass of the satellite that got treated. Yeah, so the low mass on this and high mass on the right. And this is then the number of these satellites that got accreted. And as expected from the simulations, you can see that you accrete, this is a big elliptical galaxies at the local universe, redshift 0. You accrete many small galaxies and you accrete few very high mass galaxies. So this is what we know, red from the truth. And the yellow line is really what we do through this stellar population analysis, what we can extract going through the observations. Yes. So to stress again, with Alina, we are working very hard now to really also get this out of the observation, because there's still, if you theoretically show, even through mock data, that is in principle feasible, the next step is to deal with real data where there are still systematic issues. But we are very hopeful and actually quite confident that we will be able to do this. So this is really the forefront on the stellar populations. And as already promised, I will also go through the dynamics. Yes, because in addition to beautiful maps of the stellar population properties, you also get beautiful maps on actually the motions of the stars. And so what you see here is again the same galaxy, the same muse pointings, but now you see on the top left, you see the mean velocity of the stars. Yeah, so red again is redshifted, so they're moving away from us, blue towards us. So you see that this like lenticular galaxy has clearly like rotation around this short axis. And then we can also measure the dispersion values and expect that there's most mass, there's more dispersion in the center going down to the outskirts. But these are really, really the very faint outskirts. So for the first time, we're really able to probe the very faint parts of the galaxies. Why is that exciting dynamically? Because the more you go outside, the longer the dynamical time. So the more hope is that there is information left of the past of the galaxy. And then we can also go to so-called higher order moments or deviations from a Gaussian distribution, which in a few seconds later, in a few slides, will become clear why that is essential to have them. So, but this is all nice, but we need then a technique to actually extract this dynamical information, because these are all projected light-weighted average quantities. And so now we already a long while ago, during my PhD, together with Remco van der Bosch, we actually developed this so-called Schwarzschild or orbit superposition technique. So this is very old, but I still think explains the idea. So what we do is we make an ansatz for the gravitational potential. Yes, and to keep it very short, so we have this beautiful, typically photometry, so we know where the stars are in projection. Then we, under certain assumption of viewing directions, which can be a free parameter, we deproject. So we have a 3D light distribution, and then under another free parameter, we can convert with the stellar mass to light ratio, that's to mass. Yes, and then we have the total stellar mass, and then we can add more mass components, for example, a dark component like a black hole in the center, a dark halo in the outer parts, which you can all make parameters and optimize. But the goal is for one of such models is that you have an ansatz for the gravitational potential, and then literally what you do is you calculate many thousands of orbits in those gravitational potential. And so you try out many different possible orbits the stars could move on. Most of those orbits will not be helpful. In a sense, if you put a star and you make it a light, yes, then it turns out to be that particular orbit is not helpful to explain your observations. And what is to explain your observations, for example, is to explain this stellar velocity field, or to explain all this beautiful kinematic data. Yes, so what you do is you really construct so-called orbit library with thousands, and then you do an optimization problem that you ask really of those thousands, or actually 100,000, which 2,000 are really helpful in explaining all the data. And in the end, what you then get is a grid. For example, here on the x-axis you see the radius from the center of the galaxy outwards, and then on the y-axis you see angular momentum. So 1 means perfectly circular orbits, 0 means like bulge-like orbits, radial orbits, and minus just means that it's counter-rotating. And so we picked here 3 orbits to show you. So light means a lot of weight, dark means no weight. So all of these points have a calculated orbit. Most of them don't get any weight. And then in the end, because you made a model, yes, that you can actually take these orbits, yes, and you can look at this model, of course, from the side, which is the top view, or you can look from the top, and then you see exactly what you should expect. Yes, for example, this red one orbit is not perfectly, but is going around, and it's staying in the disk here. The blue one is the same, but it counter-rotates. And for stars, this is perfectly fine. Yes, because stars never meet each other, they can just counter-rotate. Still, these stars are typically formed from gas. Yes, so, and gas cannot counter-rotate. So, like this tells you already something happened in the galaxy in the past, that now the stars are counter-rotating. And obviously from this is a very nice example, because from the stellar velocity field, you see that something weird. You see that in the disk plane, the stars are rotating this side coming towards us. If you go a little bit off the disk plane, and the stars actually going away from it. So you see that here, this galaxy consists of about 2 counter-rotating stellar disks. So this is the technique that we use. And just to give you an example, what can you do with this technique? For example, you can measure mass and also dark mass. And for example, this central black hole. You need, of course, excellent data for that. So what you see on the top, first of all, on the middle panel is again this muse. Yeah, so we are very fond of this instrument. But then if you really want to get sensitive to the black hole, you need to get the motions as close as possible to the black hole, because only those stars will be feeling the black hole actually. So that's if you need, then you need to zoom in with, for example, other instruments like symphony. Yeah? So this symphony, this field is really giving you beautiful high spatial resolution data. And you see already that there is the motion of the stars on the top, is the velocity field, on the bottom is the dispersion. And you see a very clean dispersion peak here. That gives already a good hint that there is a very high concentration of mass. And the question is this high concentration of mass really pointing to a black hole or not? And so you see here that in the end, we have also the Muse large field. Yes. So we have 3 stages. So we really go from the large field, and we need to have the large field because we first need to constrain the total mass. And then we go slightly inwards and more inwards to get more and more sensitive to the black hole. Okay, fine. So you can then measure a black hole, and you see here 3 different measurements of the same galaxy, this galaxy, with 3 different outcomes for the black hole. So on the x-axis, you have the mass of the black hole. And now, of course, the question is, which one is the correct one, or why are they different? Yes. So first of all, on the y-axis, a bit complicated, but you always have some degeneracy, namely with the stellar mass to light ratio. You can imagine like this concentration of mass in the center. Yes, that can either be because there are many typically low mass main sequence stars. Yes, you can put a lot of mass in there without adding a lot of light. Yes. Or, of course, one way to put a lot of mass without adding any light is a black hole. So there's always this degeneracy between the two. Yes. So you can break this with higher moments, etc. And but you see these ellipses here are because you can never fully break this degeneracy. Okay. So why then these differences? These differences is because we don't actually know whether the stellar mass to light ratio is constant. Just to be very clear, most of the black hole measurements in the literature just assume stellar mass to light ratio constant, because then you have a single clear parameter. However, we said, well, actually, we don't know. Actually, we can measure, because the quality of data, as I showed in the first part, is so good that we should get a handle at least on the relative change in the stellar mass to light ratio. So that we did. But then we said, okay, the typical assumption then is a fixed IMF. Yeah. So then you get a stellar mass to light ratio prediction, you put this in your modeling, and suddenly the black hole changes. But not by a lot. Like if you look at the contours, it's still consistent, but it does change. Now comes the point, actually, we don't know whether the IMF behind is actually constant. Yes, is it fixed? Is it a Milky Way or a Chabrier-like IMF or not? But I showed you in the first maps, we actually can't handle on the dwarf to giant ratio, which is a handle on what kind of IMF is behind. If we then put in this map, so we really put in the variation of the mass to light ratio because of the varying IMF, then we see that the black hole changes again. Yes, in this particular case, with this beautiful data, the black hole went down and down. We don't know yet, because we haven't done this with enough other galaxies, whether this is systematically going always to lower black hole mass. This is, of course, a very important question, yes, because are all the black hole measurements then in the literature biased in one or the other direction? And I can tell you, you can sit down and brainstorm that it could go both directions. Yeah, so the answer is, we don't know yet. We know that there will be systematic changes and there will be change in the black hole. We don't know which direction and how systematic it will be. Okay, so this is one example of this. So the other is now we can, what I show you again back to the same galaxy is with this orbit-based model that I just introduced, we can now fit this beautiful data. So on the top is the data shown before, the velocity field, the dispersion, and these higher order moments data. We make a model of it, and you can see that this orbit-based model can do a very good match to the data. The residuals in the kinematics, they are there, very interesting, but they are minimal. So, okay, fine. Then you made an orbit-based model that fits the data in very precise. Why would you care? What can you do with it? So one reason we do this very precise is because we want to have very precise mass measurement, like the black hole, as I just showed. The other reason is actually because we can learn about the intrinsic distribution, what's inside of this galaxy. And so what you see again here is a similar plot as shown before, is this circularity versus from the center to the outskirts. And to give you a reminder, so when you're up here, yes, with high angular momentum, then you talk about cold orbit. So here's an orbit shown, so quite circular and quite thin. Yes, the moment that you are at around zero, then you have so-called hot orbits. So they're kind of radial, so they're very puffy. And then, of course, in between, you can have whatever you call them warm orbits. And so as you see, what we did here is, like we all where there is color, there is orbital weights. So now you would like to break this galaxy up in certain components. You could do this, for example. You could now decide, okay, I'm gonna make, and this is really, we are now further approaching how to do this, let's say in a more statistical or more mathematical way. But the first attempt was just to make cuts, to say like every orbit that is with a certain circularity or higher, we call cold orbits. Then anything here we call the bulge, this we call the inner halo, and that we call the warm orbits. There is some reasoning. We publish papers where we say there's a reason why you can draw the line here, and it's going to draw a line there. You can go to simulations and you see really that there are valleys, yes. But to be very clear, at the moment, these are just like, let's first draw lines and see a first decomposition, what happens. And so to give you one first plot, is you can ask, okay, now I split up this galaxy in this disk, warm, bulge, and inner halo, and I can just make in principle replot what is the surface brightness. Yeah, so if you would do a photometric decomposition, then, for example, you would try to decompose the light into a bulge and a disk or more components. And so what the key point to show this plot here is that if you do make this model and you do a more physical, dynamical based decomposition, what you end up with is a bulge. Yes, it's more or less acergic, but not great, not perfect. But the key point of this plot is that the first galaxy we did, and this is holding up for many galaxies, is that the disk, yes, which you would really think of a thin disk, is exponential. No surprise. Except for the inner parts, it doesn't look very exponential, but fine. Typically exponential, yes. But it turns out to be that the warm, thick disk is also exponential. Maybe still not a surprise, but it means if you just go to the light, you cannot distinguish on the radial profile, yes. But it turns out to be the inner halo, yes. So these are really these hot orbits and large radii. So this fluffy halo is also exponential, yes. So like going through the light distribution, try to disentangle thin, thick disk, and then halo will be not possible. Yes, will be very hard. So this is one other argument to really what is the power potential power for this decomposition. So just to show you, I have shown for you now at like a few galaxies only, and you could ask like computationally, this is a very expensive method. You can speed it up, working hard on that, but fine, you do a few galaxies. What do we learn? We want to do this for hundreds of galaxies. Actually, it turns out to be that you with being smart, yes, optimizing the code and running it on Computer Plus, it has been already shown that you can do this for hundreds of galaxies. So just as an illustration, here is the orbital fractions. So again, these cold, warm, hot, and counter-rotating orbits that we saw before. And these are now measured for 300 spiral to elliptical galaxies, 149 early type galaxies, and more than 150 passive galaxies. So from different surveys, yes, it's just an illustration. This is not anymore like you do a few galaxies per PhD to say, but you can do this actually now with hundreds of galaxies. So they become feasible. And this then a summary plot to show that all these different surveys are actually consistent, yes, in these orbital fractions. And this, for example, great. For example, simulators have already been extracting this information also from the simulation because they must be able to fit and describe this. Now, is this? Yes, it works. Okay, good. So then on the dynamics, I want to show you something really, really new, which when I was here, when I left here, we said this will take many years to be able to do it. And I must say, due to a really fantastic then PhD student, now postdoc, and of course with work for many others, we think and hope to also have convinced now the community, at least we convinced the referees, that we can also make BART Schwarzschild models so that we can really also properly model, like all the Schwarzschild models before were like equilibrium models without really taking care of the bar. They were more or less in there through some warm orbits, but now we really tried, okay, so many galaxies have these non-axisymmetric features like a bar. Can we actually make Schwarzschild models of those? And so the answer is, in our view, is yes. So we've done many tests. We will not bore you with the test. Here's a real galaxy, and you see 4371. Yes, image, and then you see a Galfit model. Yes, that's if you're not familiar with it, this is a typical photometric tool. Yes, and what you see on the left are some plots to show that these fits are really working very well. But of course, it gets the complication here with the central bulge, inner disk, bar, main disk. There are many components typically to galaxies, especially if you do it even light. So to show this, the residual, so this model is pretty good. Yes, it's a good fit. And you can also show what does the bar bulge look like. You see it looks like a bar, but it is not as simple. Yes. So for example, what we quickly learned, like assuming an typical analytical profile for such a bar is not working. It's not describing good enough what real bars are. So what we do, or what Besat actually did, is said, okay, we're gonna make this is so-called multi-Gaussian expansion. This is our favorite technique. Perfect. This is you can ask afterwards, but this is a very convenient convenient way to describe components. So what we do, we pre-impose that there is a disk and that this disk is axisymmetric. So we fit this disk, yes, and then separately we actually fit the bulge components. sorry, the bar. Yeah, so the bar has a separate, as a triaxial component. If you add those two components together, you get a very good description of your light. But because we now have these triaxial and axiometric components, we can actually deproject, because this is one of the complications with such a model, is to get a proper deprojection 3D model. And again, remember, we need this 3D because this is where we build our gravitational potential from. And if we want to have realistic orbits that also describe the bar, we need to have a proper deprojection of the bar potential. So that's what we do. And then we build orbits, and these orbits now also include orbits that trace the bar. And then here's an example of the data, again, Muse data at the top. Yes, so the surface brightness, but then the line of sight velocity, the dispersion, H3, H4, and then it's being fit, and there are very low level residuals left. Okay, you would say, like, I don't see so much difference. An expert would say this still looks like a normal kinematics. So did you actually measure the bar or not? So one property of the bar that we really would like to know is its pattern speed. And so it turns out to be, I can show you many tests, but it turns out to be that you can actually measure this pattern speed quite precisely. And to highlight what typically these pattern speeds, for example, the Tremaine-Weinberg is a typical technique that's used to measure these pattern speed, but then you need really access to the disk region. And this data doesn't go very far out in the disk. It's really centralized. So the question was, how precise can we still get the pattern speed? And we did even another experiment where we even went to smaller and older data set, where we only have the very, very central part. And this was just, let's see, is there still any information in this kinematics that would hint that there is a bar needed? And it turns out to be, the answer is yes. So what you see first in red here, so on the x-axis is the bar pattern speed. Yes, that we want to know as a parameter, again, against the stellar mass to light ratio. Yes, so now you see there are rather round contours, so there's not a huge like degeneracy between them, but of course some uncertainty. So the key point to take away is that from the Muse, excellent data, you see you get very tight contours on the pattern speed. But was to us first surprising, we did some tests why that works. Even from the very centralized, you see the blue part here, data only, somewhat older data, you also get already a constraint which is consistent. Okay, so fine, you can do precise measurements with the bar without needing the access to disk. That's great, because then we have access to many more galaxies. And another point is that these Tremaine-Weinberg methods typically work for galaxies only in a certain inclination. And it turns out to be that these techniques work for many more galaxies. Okay, so then you may ask, why do you so excited to get the bar pattern speed? Yes, so one thing, for example, is that we would like to know whether bars are fast bars or slow bars. And what does this mean? This means that there is already a long-standing theoretical prediction is because of the torque between the dark matter halo and the bar, you should slow down the bar. Yes, but measuring that, of course, depends on measuring precisely the pattern speed. And not only the pattern speed, you also need to know the size of the bar. And so the size of the bar typically came from the photometry, some technique, and the pattern speed from this Tremaine-Weinberg. So without going into details, with the Schwarzschild model, you get all at once, which means that you exclude some of the systematic effects. You get it not in projected, but in intrinsic quantities. So you can get a direct measure of this so-called R parameter, which is the co-rotation radius, which depends on the rotation speed and your pattern, or your bar pattern speed, and the size of the bar. And it turns out to be, for this very first galaxy, immediately this R value, as you saw, is well above 1.4, which is decided to be, that's a slow bar. Yes, and it turns out to be that this galaxy also has quite a high dark matter fraction. So this would be one of the first few galaxies where there's really strong indication for slow bar and significant dark matter. So it might indeed work. Of course, what we're trying to do now for more galaxies, and especially galaxies with very low dark matter fraction and very high dark matter fraction, do you find that this R value is different? Okay, so to end, yes, the last part is combining the two. Yes, and that is what we really get excited about, and the possibilities. And this is for example, can we now go back to the question, can we find out like whether there was a past major merger in nearby galaxies? And you might have seen some results on the Milky Way. We found this Gaia Enceladus sausage, whatever you want to call it. This like 8 gigayears ago, a last major merger with the Milky Way. And then in Andromeda, we have also through resolved stars, like we found out that was also this a major merger, actually a very massive merger, but that massive merger happened only 2 gigayears ago. Yes. So another question is, and of course the answer is yes, because otherwise I wouldn't put that slide. Can we do this now for nearby galaxies? And so here again to the same galaxy. Yes. So it's the same Schwarzschild model as before, nothing special. Now we also, on top of that, what we do, we add stellar population properties. So we have all these orbits. Yes, they were first just populated with light. Now we start saying that all these orbits, these are stars, they should also have an age and they should have a metallicity. And then populating with age and metallicity, we're going to fit actually these beautiful maps that we measure the stellar age and the stellar metallicity. And yes, it works. What do we learn from this then? So what we get is these kind of complicated maps. Yes, the left one is the one we saw before. It's just the light distribution over the different orbits. So disk, warm, inner, and bulge. But now we can actually know for each of these orbits, what is their age and what is their metallicity. And these diagrams are difficult to read. So we can, for example, extract like the profiles. So we saw, for example, the surface brightness profile. I'm highlighting here this inner halo part. So you see, okay, it's an exponential, already told, nothing special. Then you see the stellar age, you see overall there's a very old inner halo. Yes. And then you see that also this is the least metal rich, but still water metal rich inner halo. So why are we so, and this is just for the people that are excited about upturns in disks, but we can discuss that later. So focusing on this inner halo, why are we so excited? Because then we went to simulations with Anneliese Pilipic. We selected all the galaxies from the TNG50 that have a similar now size and mass, nothing else, no other selection criteria. We extract all of those, we make mock data, we go through the whole machinery, and then we ask what happened actually with this galaxy. And it turns out to be that such an inner halo, you can only explain from a major merger. Yes, from a past major merger. And that means that through the simulations, we can actually start by measuring its mass very precisely, because we can identify the orbits, we have the weights, we can show from the simulations that there's actually a tight correlation between the mass of the most massive merger that this galaxy had and how much the stars are deposited in this inner halo. Yes, and so now you can get an estimate for this observed galaxy of what was likely the mass of the past major merger. So more exciting, or equally exciting at least, is that we also have the timing. So we have the age of the stars, and it turns out to be that we can actually use that age of the stars. So now it's the same circularity. So disk orbits, bulge orbits, counter-rotating orbits, but now plotted against their age, because we have each of the orbits colored with age. And what to take away from this is a simulation. Yes, this is all a mess. Yes, these orbits are going everywhere and they're hot. It's no wonder, because we can go back in the simulation and see that around this time, yes, a little bit before, it had a major merger. So it was unhappily actually spiral-like galaxy, and then boom, like all the orbits were actually like put on all kind of like different orbits. So all these nice cold circular orbits, they were moved to everywhere. Yes, until the merger was over, there was gas remaining, the gas settled, and the gas then forms. It likes to form disks, yes, and it forms stars from that. And then you see nothing happened with this galaxy further, no major mergers and so nothing in the inner parts, and it just keeps on these stars which are on happy circular orbits. Yes, so this change from a mass to organized actually identified when the merger ended. Yes, and it turns out to be, if you then make a mock data and you go through this whole machinery Schwarzschild modeling with this age tagging, then of course it doesn't look as beautiful as the simulation, but you still see this transition happening, but smeared out. Okay, and here is the real data, and we get the same kind of transitioning in this real galaxy. So what we do here is we say, like, based on the simulation information, that is when this galaxy had a major merger. Yes, it ended around this time, because after that, yes, all the stars that are younger than that are happily on a very nice rotating disk. And so this then, this in principle gives you the mass and the timing of the past major merger. Yeah, and okay, why this is similar techniques used here as in the Milky Way, because you might have seen this plot from the Gaia Soch and the Lada again from this last major merger. Yes, and especially the right one was for us very interesting, because it shows the kind of like circularity for individual stars in the Milky Way versus the age. Of course, they plot Big Bang here and now there, while we did the other way around. But the same effect happens, yes, until like 10 gigayears ago, a big mass, and suddenly many of the stars are on the reformed disk, so they are much more organized. Yes, and so the timing is of the major merger ends. So this is like a way of getting the timing in the Milky Way also of Gaia and Enceladus. So this is just to show you that what is done in the Milky Way, we hope to convince that it can also be done in nearby galaxies. Okay, so then a completely independent, or not completely, but an independent way to show that this 10 gigayear past major merger is not completely crazy is a work from Ryan Lehman, because he says, okay, so you have all this beautiful data. Yes, I have this beautiful model, semi-analytic model, where if you tell me your star formation history and only the star formation history and the current total stellar mass, I can predict to you what should be the velocity dispersion of the stars that are born from the gas at a given time. Yes, so you go back in time, yes, and you say, for example, the very old stars, 12 gigayear old stars, were born from gas in red that was with a typical velocity dispersion of 60 kilometers per second. Even older back in time, his model predicts that it should be higher. And if you go to the more younger stars, this dispersion goes down and down and down. Yes, it becomes less turbulent, the gas from which the stars are formed. Yes, he predicts that with his model. And what you see in black, so in the points, is what we measure then directly from our Schwarzschild model, because we have the ages of the stars, so we can select all the stars in the disk. Yes, currently in the disk, and you see that they match quite well. But these are only the stars, or the orbits in the cold disk. Yes. If you then actually measure like stars that are outside of the cold disk, so in the thick disk, you suddenly see that the dispersion, it goes up dramatically. Yes, it matches perfectly well the younger stars, but it goes up dramatically. And why? Because at 10 gigayears, the reason for this is at 10 gigayears, this merger happened. Yes, so the stars were happily born from the gas. So they had like whatever 60 kilometers per second. Then this major merger happened, and boom, they got like kicked up to a much higher velocity. So this is just to give you an indication from a completely different angle that we believe we come to the same conclusion, that this galaxy had a major merger 10 gigayears ago, and it's about 1/5 of its current total stellar mass. So this is like the end. I just wanted to briefly highlight you, okay, we showed mainly one galaxy, yes, And the reason for mainly showing one galaxy, because of course this is a lot of work, but because it's also very computationally expensive. And that's why we're actually now working with mathematicians in this SFB. So this is this Sonderforschungsbereich. It's a similar one as here in Germany, where we have the mathematics to help us to speed up. Because if we want to do this for more galaxies, we need to speeding up this whole technique. And actually, it's a very interesting combination because these mathematics with their models also help out people in medicine and in physics. And I'm happy to talk about how that gives also very interesting discussions more around the table. And then the very last slide, completely different. Yes, is what we are getting more and more excited about is the gravitational waves, and particularly the Einstein telescope. And I just want to put a little bit promotion here, highlight that the doctoral school vices that Nadine mentioned. So we will, as part of the doctoral school, we are organizing a summer school in 2025. So not this summer, but in a year from now. And if students are interested, then please come to me or look out for the advertisement. And finally, of course, this is a work of a whole team and a whole collaboration. I'm just showing here the people that are currently the PhD student and postdoc and one software engineer that are currently in the Vienna group. And I think this is a group effort, and I'm really, really proud of how nice this working all together. And last but not least, we are making this code that we use publicly available in steps. So this is a lot of work, but I think this is something that we have to do more and more and give back to the community. It's an effort, but I think it's worth it because, for example, I just saw a paper where it's completely independent from our group of collaborations where they actually use the code, and that I think that is really an investment and a return back to the community. Thank you.
Well, thank you for this absolutely fabulous colloquium. I'm sure we can all recognize that. And it's amazing to see how you can derive such sophisticated physical information from these telescopes. I mean, that's just an amazing thing. And also how from the other direction, you can match it with the simulations. So I'm going to open the floor for questions. If you want to ask questions from online, please type a message into the chat. And right at the back, my first test.
Thank you. How do you derive the ages and what is the typical precision of the ages?
Yes, so I can just answer that. The typical precision depends on how far you go back. Yes. So if we really talk about these older ages, then getting it better than half a gig a year is complicated. Yes, that's also why this spread that you see here, yes, is mainly driven by uncertainties in the measured ages. And how we derive it through this technique I showed at the beginning, through this full index fitting. So this is principally like stellar population model libraries, yes, that are in detail fitted to absorption features, but then within the absorption feature, pixel by pixel, so to really get the details of the absorption features matched.
Oh,
yes.
Dylan Nelson.
Actually, I had a very similar follow-up question about the spectral fitting and moving to full spectral fitting as opposed to index-based. So do you think this would be useful, or do you think you're capturing most of the information already with the index approach?
So full spectral fitting. So first of all, it's for pragmatic reasons. Yes, the full spectral fitting just takes too long. If you want to do this for, well, here are 50,000 spectra, it's just not going to work. And secondly, you can indeed show that most of the information is actually in these features, in these absorption features. So you don't gain a lot by including all the pixels around it. Yes, aside from that, even dangerous that sometimes you add regions of the spectra where there are systematic effects. Yes, so it can also help with cleaning out certain regions which are affected. But we did comparison with full spectral fitting versus this like full index fitting. And obviously it's much stronger pixel by pixel than if you do like an average index feature, because that's never gonna be able to extract that kind of information.
Can I ask really quickly also about the spectral libraries? So,
Yes.
in your opinion,
Oh, that's a
coming in there,
could
especially with
easily,
IMF variation.
Yes.
And where do we go with that? Yeah.
So I'm absolutely not the expert, but I learned that this is a very tricky question. So I can, of course, now say, well, ask my collaborators, but the spectral libraries that we are using, there are enough people in the team that are very critical about this. And now we're trying to also do this for, these are all early type galaxies. So these are relatively simple, but we're now pushing this also to star forming galaxies. And then we very quickly learned you have to be extremely careful with expanding your stellar library to younger ages. And so there was a recent paper by Martin Navarro, which I think is now published, but if you want, we can tomorrow, I think we're meeting. I'm more than happy to show you in more quantitative way. So yes, we are very much aware that the question you're asking is a critical but difficult one. Yes.
Ralph Klessen.
Very nice results, really fascinating. I guess my question is similar to Dylan's question. I was wondering about extinction and how it distorts your spectra and spectral indices. I mean, for these galaxies, you have very little gas left, but for some, you have much more.
Yes.
And
so, the answer is, the honest answer is that this is a project that we're working on. Yes, because there's this fantastic data set, and not we, it's mainly other people, it's the generous we. In that there is this GECKOS data set, which is targeting edge-on like star-forming galaxies. Yeah, so if you're asking for trouble concerning extinction, then it's these galaxies. But there's also an opportunity to show how we can deal. So from a kinematic point of view, even if it's surprising. If you look at the stellar kinematic maps that come out of these like very dusty edge-on galaxies, it's still very limited like rubbish or distortions that you see in the stellar kinematics. Yes, and so, but there is, you start detecting. So there are a couple of ways to deal with it. In the past, they just cut out anywhere where there's dust. Yes, and then make your model, and it still typically works well as long as you have good enough data outside of the dust region. Yes, because the nice thing about dynamics is that it couples all the spatial directions. Of course, the very thin cold orbits, you're cutting out all the dust region you're missing. Yes, so that you're then adding this artificially. So that is one approach. That that's the generous we, that other people are doing, is actually modeling this in. And so you can imagine that in top of age and metallicity, yes, why can't you not add like to these orbits a kind of like extinction? So that we already tried way back during my PhD, yes, with Remco van der Bosch. And yes, it was hopeful, but to have this then as a free parameter that's disastrous for your computational method. But in principle, you can add this to your orbits. You can add a extinction. We just don't know how to do it pragmatically yet.
what about going to different wavelengths?
Yes,
Infrared?
of course. I mean, so with CALIFA, for example, we had the kinematics in the blue part. Yes, in the optical, and we said, okay, we don't care about the dust because we get near infrared images. Yeah, so we put in the proposal, we get the near infrared images, and we're all happy because suddenly it looks much more like stars. Yes, and then we figured out that we forgot one obvious thing, is that we have our kinematic tracer in the blue optical, and we get our tracer density from the red. Yes, near infrared. Because you can solve the Jeans equation. You can look at the Jeans equation. Yes, there's a tracer density and there's the kinematics. If they don't come from the same wavelength, you're probing different populations. And so in the end, with the CALIFA, it turns out to be it's better than to stay in the optical, deal with masking the dust and try to still get your best smoothed tracer density in the optical, yes, than going to the near infrared. Of course, the solution then is like get the kinematics in the near infrared also, yes. I mean, that is, but like Muse, etc. Most of these instruments are the powerful ones are still in the optical. So now about dynamics.
I've a comment on the or questions about the Schwarzschild models for bars. By the way, we did that 24 years ago for the Milky Way.
Yes.
And of course, the constraints are easier because we know better where the bar is. So you have more free parameters, orientation of the bar. And so one question is, how well are these free parameters or these parameters termed? But the other issue is I'm worried about applying these models because Schwarzschild models per se are equilibrium models. The basic assumption is equilibrium. Bars are per se non-equilibrium. The slowdown cannot happen in equilibrium. And it is the non-equilibrium is of the order of 20% or something. So you get 20% errors then. Is that not what you expect? Or how can you do this?
Are you joining for dinner? We can. Good. So yes, of course. I mean, just to acknowledge, yes. I mean, you were involved in a study where the bar model, Schwarzschild-like bar model of the Milky Way was done, but I don't think it was done beyond the Milky Way, as far as I remember. Yes. So yes, of course, we are worried about the non-equilibrium part, but not only for the bars, but like in the Milky Way, we clearly see that there are clear indications in the kinematics from non-equilibrium. Yes, so we will always have to keep in our mind these are equilibrium models, and there will be non-equilibrium features. The question is how much are, for example, the bar pattern speed biased by this? Yes, and this is what we tested on the simulations. There you can make mock data, and it turns out to be that within the error bars that we have, and I can go back to the plot, there is actually not a bias. So, and then we can discuss whether is it because we don't understand what is actually happening, or whether this is because the Schwarzschild model with the orbits is somehow able to compensate for this this non-equilibrium. It's anyway still making a snapshot of the situation. Quite a bit, but maybe not enough. That's what you say. Yes.
Okay.
Very interesting to talk about.
Okay.
Yes.
That's going to be a question for dinner, I think. The final question of this semester goes to Saskia Hecker. Sorry.
Okay. That's fine. Yes. Hi, nice to see you.
Nice to see you. Fantastic talk. Hopefully a quick question with a quick answer. About the possible bias in measuring the mass of the supermassive black hole, if you don't use the right IMF or mass to mass ratio. Are there any galaxies in your sample or that you can target where you can use different indicators to get the mass of the black hole, and so you can benchmark?
So Sabine
benchmark the answer.
actually the person behind this study. So she did main part of her PhD was comparing molecular mass black hole measurement based on molecular gas kinematics with stellar kinematics. So in her sample, yes, she has these different independent ways. And then it would be really great if we can also use the maser measurements, yes. But there we try to get stellar kinematics, or we have stellar kinematics for one of the maser galaxies. And the moment you start plotting the maps, it's horribly complicated, yes. So not unexpected, but it will be hard working to get that done. But in her sample, at least there is the molecular kinematics that can be used as an independent one. And she showed already, depending on your assumptions, not surprisingly, you get biases, but you can actually now learn by comparing the two. Because in both techniques you make assumptions. So the key is to figuring out where can you get it to match.
Okay, great. Well, it's nearly time to wrap up. Before we thank Glenn, could I make a couple of announcements? So once again, Glenn, that was a most fitting end to our colloquium series, and it was quite amazing to hear about all these results. We wish you all the best. If you come back in another 10 years, maybe we'll have the impression that you've solved the universe. Let's see. Thank you again.